Alright, so here we are looking at part 2 here. Part 2 here, we're going to first start with a proof, and then we're going to get to a couple of examples, okay? So we're going to prove part 1 of this theorem. So the proof here is going to be as follows. We have a circle, and we have inside that circle. Alright, so sorry, I just got a phone call and I lost where I was. So we have a circle. We have two chords inside that circle. And we are trying to prove that this length, we'll call it A, times this length. We want to prove that AB, or A times B, equals C times D. Well, how do we do that? Let's look here. There's a couple... there's a few options, but one of them that I particularly enjoy, because it connects to what we've been doing before, is creating two triangles there. So you're going to draw two triangles, right? Now let's call this point capital A, capital B, capital C, capital D, capital E. So we've created triangle A, let's call it CB, because we go to the center there, ACB, which I just outlined in black, and then we also have created triangle ECD, right? So ECD. So we have two triangles there. Now, we know that angle ACB and angle ECD are congruent because they're vertical angles, right? So we have vertical angles. We also know so let me just write that first. So angle ACB is congruent to angle ECD by vertical angles, right? Vert angles. We also know, now we're going to use some of our arc knowledge here. We know that since angle B, or angle ABE forms this arc AE, and angle, let's change colors here, angle EDA also forms the same arc AE, that we can say that angle ABE is congruent to angle EDA, and that's because they are inscribed angles. So how do we know this? Inscribed angles form the same arc, right? The inscribed angles that form the same arc are congruent, which means we could then say, so we know this is congruent to this. So we have two triangles with two similar angles. So we could say then that triangle ACB is similar to triangle ECD by the angle-angle similarity postulate. So when you know the triangles are similar, that means that their side lengths must be proportional, right? So the side lengths must be proportional. Let me make some space up here. Side lengths must be proportional. So what does that mean? And if I just erase something you're trying to copy down, just rewind, no big deal, something in the world, right? So I know that the side lengths are proportional. So one of the side lengths, A, over, what's the corresponding, I'm going to write my last, what did we have before? ACB, ECD. So that's my roadmap. ACB, ECD. So triangle ACB is similar to triangle ECD. That's my roadmap. So I can say then that lowercase a, which is AC, the first two letters, right? First two letters, over EC, first two letters, that would be over D. Those are corresponding sides, equals what? Well, I have C, which is BC, right? So it's the last two letters, over CD. What are the last two letters there? That's length B here. I covered it up, but there's a B right in there. And then this is, by definition similar, right? So definition, oh, that's an arrow, my fault. Definition of similar triangles. Then just cross multiply. You have A times B equals C times D. And that's property of proportions. And you're done. Happy face. Yay. We've proved something. So anyway, so that concept works. If you want to, you can try to prove parts 2 and 3. Again, you're going to want to use triangles. You're going to want to show things are similar, and that's a wonderful strategy to use. All right? So, here we go. Let's look at some examples. In this example here, we need to solve for x, and we need to solve for y. So when I'm solving for, first of all, there's a couple key things here. This point on the side here is one of the intersection points, and this point in the middle is another intersection point. Those are the key points you want to look at, okay? You want to look at those, because those are the ones that this theorem applies to. If I chose this middle one and look at the lengths from that point, I have y times 9 equals 5 times x, right? Because this length and this length, again, along the same length. It's just a direct application of our theorem. But that leaves me with two variables, which I don't want. I don't want two variables in one equation, because then I can't solve for anything. So that's actually a bad option to start with. Okay? So what I want to do then is start with the other point. So let me erase this stuff here, clean up the picture. I'm going to start with this other point. I'm going to say one of the side lengths is 11 along the same path. Since it's tangent, I get 11 again, so 11 squared equals, let's follow my other path. Well, I have 7, right, equals 7 times, what else is along that path? 7 plus x plus 5. So now there's 3 side lengths there I'm adding together. I get 7 plus x plus 5, which don't panic, because 7 and 5 combine to make 12. So this is 7 times 12 plus x equals 121. 7 times 12 is 84. Right? 84 plus 7x equals 121. Subtract 84 from both sides. You get 37, I want to say, equals 7x. And divide by 7, you get x equals 37 over 7, which is not that nice of an answer, but that's okay. Now, I can go into the circle now to solve for y. Now that I know x, I can solve for y. So again, starting with this point here, one of my paths will be 5 times x, or 37 over 7, equals other path, 9 times y. Right? Well, 5 times, this is 5 over 1 times 37 over 7, so that would give you, what is that, 185 over 7 times 9y, or equals 9y, sorry. Divide both sides by 9, and you get 185 over 63. If you don't know how I did that, another way, instead of dividing by 9, just multiplying by 1/9. 9 times 7 is 63. And that's your answer. So y equals, barely fit in there. There you go, 185 over 63. All right, one more for fun. Just for, we're done after this, I promise. Yeah, nothing after this, so you're good. So, last one. We have problem 24 here. It says we need to solve for x and y. Now there's two circles involved. This segment x of length x is tangent to both circles. Okay, it's tangent to both circles. So let's deal with the top circle first, because there's only one variable there, and then we'll deal with the bottom circle later. So once we get x, we can solve for y. So the top circle would give me x squared equals 4 times, so again, how we got the x squared was this length times itself, equals 4 times this whole length of 20. So we get x squared equals 80. Again, from part 1, you should remember this is 16 times 5, right? Which is 4 times 4. So you get x equals 4 rad 5. Once you know x, you can solve for y. Same concept. X squared, x times x, equals 8 times 8 plus y. Now, don't overwhelm yourself with, okay, 4 rad 5 times 4 rad 5. Because you already know that what did you take the square root of to get the 4 rad 5? You took the square root of 80. So x squared is 80. It's written here. So this you know is going to become 80. X squared is 80. So 80 equals, distribute here, you get 64 plus 8y. Right? Subtract 64 from both sides, you get 16 equals 8y, therefore y equals 2. And you've got your answer. All right. Bueno. Well done. Good job. Another section down. Again, always recommend do practice problems. Check your answers. Look up, I mean, if you want, you could even Google. If you don't have a book to look at, Google some, do some more practice problems, make up your own if you want, right? You just draw a circle with 2 lines through it and give them numbers and see what happens from there. Anyway, see you guys. Enjoy the rest of your day. Bye.